Day 10 of our INBRE workshop here. Today we are going to be talking about survival analysis. I'm so excited to be talking about survival. I've had a great opportunity to teach a lot of courses since I've been at the University of South Carolina. Survival analysis is one I've never had the chance to teach, and it is a topic I really like. It's actually my dissertation was in survival analysis, so it's really my first research area focus. So this is my first time teaching it, so I get a whole day to talk about survival analysis. So I'm excited about that. I am going to share my screen here to get our documents together. What we're going to be using are the slides for day 10, and then this document here, the day 10 survival analysis HTML. All right, let me get my camera windows, Zoom windows, kind of where I like them. We all have different places, I'm sure, where we like the windows and everything. Okay. Make this a little bigger if I can figure it out. There we go. Okay. Get my maximize. Okay, so survival analysis. Now, I always like to start with a little bit of history about what we're talking about here. Survival analysis goes way back. It's, one of, I don't know if it's I think it might be the earliest statistical method that really came out. The 1660s was the first time the beginning of survival analysis. First time anything was published, at least, was the 1660s. May have been even been before that. How you even publish in the 1660s, I don't know. I don't understand how that works. But it came from the actuarial field. This is before modern medicine, way before. And what was published was life tables. So it was really a table year by year, how many people lived to that age, how many people did not live to that age. And just getting that data, not any analysis or anything like that, just really getting that data was amazing. And it was used to estimate how long a random person lived. First off, crazy, 1660s, they could do this kind of thing. They found that females lived longer than males, and also that the early death rates, obviously 1660s, there was a lot of infant mortality. So survival goes back a long ways. Back farther than linear regression with continuous outcomes, which we talked about Monday and Tuesday, before any logistic regression with binary outcomes or hazard ratios, which we talked about Wednesday and Thursday. But this is really the third main type of outcome that you'll study in statistics, okay? Continuous outcomes, binary outcomes, survival outcomes. Survival outcomes are a time to some event. How long until a cancer patient dies? How long until a transplant recipient rejects an organ? How long until a patient experiences their first coronary heart disease event? How long until a bacteria develops an antibiotic resistance? The event that we see could be death. It could be recovery. It could be disease onset, relapse, discharge, any transition from one stage to another. One question, we have this time to event. Any thoughts on why we would not just use linear regression in a situation like this. It's a continuous outcome. What are some of the issues that we could have with linear regression? Okay, maybe it's not obvious. We'll come back to it. Okay, we'll come back to it. Why we wouldn't use linear regression. So one thing that's unique about survival analysis is something called censoring. Survival has a start date and an end date, but not every participant has a start date and an end date that we observe. Um, what can happen is that the event time, the end date often is censored. We don't observe it. We only know that it exceeds some particular time. So for example, when the study ends, all the participants that have survived until the end of the study, they are censored at that point. Other times, a participant is lost to follow-up. We don't know what happens. Other times, if we're looking at death due to cancer and somebody dies in a car accident, that's not, they didn't die because of the cause that we're interested in. They died of a separate cause. So again, we just know that they did not die of cancer up to the point where they died of something else. So a lot of reasons for censoring that can pop up. The important thing is these data are not, they're not missing. We don't want to get rid of them. If we know this person lasted, survived a year, 2 years, or 100 days or 200 days, that means something. They survived 100 days. They survived 200 days. That tells us something. We can't just get rid of that information. So this is one of the, and probably the main differentiator between survival analysis and the other outcomes that we've gone over is this censoring issue that we have. If we were to drop these, we would have biases in our analysis, and we'll kind of go through that issue. So this is a graphical look at all the different ways that censoring can impact our analysis. So we have the start of the study here with this left blue line. Okay. Participant one, we see, okay, let's say we're looking at survival with cancer. They got cancer at the start of the study, and they died before the end of the study. So we know their start time, we know their end time. The second person, okay, we see their start time, the study ended, they were still alive, and they died soon after the study ended. Person three, we have their start time, they were still alive at the end of the study, and they were still alive much longer than that. We don't even know when they died. When we have right censoring, these two individuals are going to be treated the same way. Oh goodness, what did I do here? Let's see if I can get rid of that. These two individuals are going to be treated the same way. We don't know that this person died soon after the end of the study. All we know is that both of them were alive when the study ended. So our information for both of them, let's say this was a 5-year study, is that they survived for 5 years. We don't know this person died, that this person lived, anything like that. All we know is that they survived for 5 years. Both of these participants, 2 and 3, they're both censored. This is what we call right censoring. So the information on the right is what we don't know. We just know that their event was larger than they died after a particular time point. This is what we will be focusing on here today, right censoring. And really that's because that is what I would say 99% of analysis have is right censoring. We don't commonly see these other types of censoring that we'll talk about. Um, the other two types of censoring, one is left censoring. So here we have a person, we know when the person died, but we actually don't know when they started. We don't know when actually they started to when they started to become at risk for death. So if here we have this is a cancer study, we don't know when this person got cancer. We just know that when they came in right here, they already had cancer, and then they died right here. This is called left censoring because what is on the left is unknown. Um, so before I came to University of South Carolina, I was at the National Institute of Child Health and Human Development. And there we did a lot of time to pregnancy studies. And these studies are designed we enroll a bunch of couples, we follow them until they get pregnant. So there we're interested in our event would be the woman getting pregnant in the study. Now, these are hard studies to do because we have to enroll participants. Okay, we got to find couples that want to be in our study, and usually we're finding couples like, hey, you want to be in our study? Yes. Okay, great. The study's going to start in 2 months. Um, so these people that are enrolling, they and their partner, they want to get pregnant, but we're saying, all right, you're not going to get into the study for a couple months. So don't try to get pregnant for a couple months. How many couples do you think are going to actually say, well, let's not try. Let's respect the study and let's not try to start getting pregnant until the study started? Not many. So left censoring was something that was a big issue for us in those time to pregnancy studies because couples would be trying to get pregnant before they entered the study. Um, this created some biases in our sample. But so left censoring, it does come out not nearly as common as right censoring. Um, in fact, interval censoring is actually more common than left censoring. So interval censoring is when you know the event occurred in some interval. This actually happens pretty commonly. Particularly when your event is something that it takes like a test. Okay, you have to be tested for antibodies maybe, and we know that okay, at this test you didn't have the event. At this test you did. It happened somewhere in there. Maybe there's a 3 month interval, and we know okay, your event happened somewhere in that 3 month interval. That's something called interval censoring. So that happens more commonly than left censoring, but right censoring by far the most common type of censoring and the one that will exclusively focus our study on today. Okay, any questions about censoring or anything? Just okay. Shrinking of the population. Yeah, so our population it does shrink. It shrinks, particularly because two reasons. Well, we have people dying, but then we have people dropping out or dying due to other causes. We'll see this when we start estimating some qualities of our data. We have a lot more uncertainty as a study goes on. And really the most quality information from a study will be early on. So it is kind of something that we have to be careful with when we're modeling what's going on later on. Sometimes that can be an issue that we need to deal with on the analysis side. So yeah. Um, okay, so oh, Chad, I see you were probably answering my first question when you said shrinking population. You're right. Yeah, yeah, the censoring did a shrinking population. Good point. Okay, so why don't we do linear regression and logistic regression? What are the issues with these? Uh, use linear regression on observed time. Well, the problem is the censored observations are not they're not observation times. So if somebody is censored at 5 years, what are we going to do with that five? That does it go into so it's just the censored observations, uh, uh, they're not real event times. So if we treat them as such, it's going to underestimate survival. If we treat them, if we ignore them, we're also creating biases, also underestimating survival. So there's no natural way to incorporate censored observations. The second one is survival times are typically right skewed, not normal. So this is also another issue that nothing we can really handle usually. So there is a method called the AFT model, and what the AFT model is similar to linear regression with survival data. We're not going to talk about that here today. We'll talk about the Cox model, but the AFT model is one and it that has controls for censored observations, and it has some things to control for the right skew. This is probably what most people would think to do is to use a logistic regression on did the event happen. Um, there's two issues with that. The first one, this ignores the time dimension entirely. So let's say we did an analysis and we said, all right, our event is going to be did they survive 5 years? Okay. Somebody who dies on day 10, no, they did not survive 5 years. Someone who dies on day 1000, no, they did not survive 5 years. So they go into the analysis as the same thing. They're just a one. Neither person survived. So we're throwing away all the information that, wow, these two are actually really different. So you're losing a lot of power when you're doing things that way. Another issue is, let's say someone was in your data and they were censored at 4 years. Well, did they survive 5 years? We don't know. Maybe they did, maybe they didn't. So another issue with logistic regression is that how do you handle censored observations when they are censored before whatever, however you're defining your event of interest. So logistic regression is not a way to do this either. Okay, so the example we're going to use for this lecture, we have it's patients with advanced lung cancer from North Central Cancer Treatment Group. I think we can go over to our notes here to get into that. I'm going to open up the QMD file as well so we can run some of these things. In particular, some of the figures, I think it would be nice to look at a little larger. I'm just going to load in. So we haven't used the survival package before, so that may be one that you have to install on your computer beforehand. I'm just going to run in this long data. Okay, good. So the first thing we're going to do is we're just going to look at this data a little bit. We're not going to do any analysis to start with. So this data is built into R, and it has 228 individuals on it. There's a number of variables that we have here. Institution, this is a grouping variable. We're not going to use this one today. Second variable is time. So this is days from study entry to death or censoring. So this time variable does not differentiate whether somebody died or somebody was censored. It's just the number of days that they were in the study. And this is commonly how survival data will come in. This is the main variable that we have. With that, we will have a status or a censoring variable. Here, status is equal to 1 if the person was still alive at that last time of contact, and 2 if they were dead. So if we look at these first 3 individuals, how long they were in the study: 306 days, 455 days, 1,010 days. Status 221. So that means the first 2 individuals died in the study at 306 and 455 days. The third individual was still alive at 1,010 days. So when the study ended, they were still alive. Some other variables. Sex, of course. Okay, male, female. Age, years in years at entry. ECOG performance score. It's rated by the Foley, rated by the physician. This variable is 0 if the person was fully active, 1 if they were restricted but ambulatory, 2 if they were in bed less than half the day, 3 if they were in bed more than half the day. So it's a categorical variable, just some basic information about the health of the patient in the beginning of the study. So it kind of gives us some indication of how, like, what this person's health was when they started. We also have 2 others. These are the Karnofsky performance score. It's 100 if they are normal, and it decreases with worse function. So there's 2 versions of that. We can see those variables here for the first few participants. The next variable we'll consider is weight loss. So this will be weight loss in the 6 months before the study entry. So another indicator of how healthy the person was. This one, the first person has some missing data in there. And then we see how much weight loss we had as for those first few participants. Like I said, 228 patients. Let's check the overall event rate. So here we're going to count status. This is going to give us how many were censored, how many were dead, apply a label to it, and get the percentage of that rounded. So 63%, 63 total patients out of 228 were censored. That's 27.6%. The remaining 165 did die in the study, which is 72%. So this is a pretty high event rate for a survival study, which is typical for advanced cancer. We will have, if you see studies that enroll people early on, you won't see event rates this high. So let's take a look at these data, get some means and medians for the data that we have. Some naive approaches to getting mean or median. The first naive approach is here we drop censored patients entirely. So we're filtering by status equals 2. So we're only looking at the 165 patients who passed away. Median survival time is 226 days when we do that. Second naive approach is to treat censoring time as an event time. The median time increases by 30 days versus the first method, but this is also, both of these are going to be underestimates of the true median time. When we drop patients entirely, we're creating a biased sample. So then we're only looking at the median time to death among people who died in the study. So that's an unclear population. The second one, clearly, a censoring time is not an event time. Okay, the event times for those who would be censored would be larger than the censoring time. This first person, third person in the study, 1,010 days, and then they were censored. What was their true event time? We don't know, but we know it was larger than 1,010 days. So this is going to underestimate survival. This is also going to underestimate survival. Both of these versions are going to do that. Okay, let's go back to the notes and talk a little bit more about what we will be estimating here. So when we do a survival analysis, our main focus is the survival function. This is usually denoted by S of t, and it's equal to the probability that the survival time is greater than whatever value we're looking at. So if we look at S of 30 in the study, that would be the probability somebody would survive longer than 30 days. If you look at S at 300, what's the probability that someone would survive longer than 300 days? These are mainly what is going to be of interest. What are the survival probabilities? What's the problem? So if you've ever had a loved one have a tough cancer diagnosis, some of the first things you hear, what are the 5-year survival probabilities? What's how many people with this particular cancer diagnosis survive 5 years? Some of the properties of the survival function, S of 0 is equal to 1. Everyone is alive, event-free at the start. And from there, the survival function is non-increasing. It can only stay flat or go down. It can't go up. S at infinity is equal to 0 in theory. So at some point, everyone is eventually going to die from the event. There are some models that relax this. You can have some, if your survival event, for example, is death due to skin cancer, you can say, well, some people would never die of skin cancer. So there are some models that relax this, but that's beyond our discussion here. The survival function completely describes the time to event distribution. It's all that we need to know. So our first method that we'll go over, we'll look at estimating this survival function. Another important function in survival analysis is the hazard function. This is commonly denoted as H of t. Sometimes it's denoted by a lambda of t. Either one of those, they usually will denote the survival function. What is it? It's the instantaneous rate of failure of an event at time t given the event has not occurred. So you can think of this as it is a rate of failure. So what is the rate of events at a particular time? But it has this conditioning. So it's what is the rate of events at, say, 1 year, given people are still alive at 1 year? What are the rates of events at 5 years, given that they have survived 5 years? So it is an instantaneous rate of failure. So at a particular instant, what is the rate of failure given a person is still alive at that value or at that time? It's the rate of failure can be greater than 1, so it's not a probability, so to speak, because it doesn't have that 0 to 1 stipulation on it. What we'll be doing is we'll be comparing hazard rates. particularly when we get to the Cox model later on. We'll be doing regression on these failure rates. So some examples of different hazard shapes. So what is going to happen to the hazard? Let's think about that. The first one, the hazard can be constant. So this means that the rate of failure does not change with time. This corresponds to something called the exponential distribution. And this sometimes is something that people use. So the rate of failure is always the same. Another one is an increasing rate of failure. So the risk grows over time. This is something that can happen with cancer or aging. So the longer you survive, the higher the instantaneous rate of failure is going to be. Can be decreasing, so high risk, high rate of failure early on, and then dropping. Certainly in post-surgery complications, if that's what we're looking at, we're going to have a high risk of those right after the surgery, and then a month, 2 months, 6 months, a year down the road, the rate of failure is going to be very low. Another one that occurs is the bathtub rate of failure. So this is one that is sort of high early on, low in the middle, and then starts to creep up a little later on. So kind of looks like the shape of a bathtub, right? Where we see this in one situation is human mortality. So we have that infant mortality early on here. So the rate of failure is going to be high early on, but then it's going to lower way down, and then it's going to creep up as people get older. So those are some examples of hazard rates that we can see in practice. We're going to come back to the hazard function later, as I mentioned, when we talk about the Cox model, and we're doing regression. So survival regression commonly is something we do with the Cox model. With the hazard function, we'll get into hazard rates, all those kind of things. Before we talk about that, we're just going to talk about how to estimate the survival function. And for this, we are going to use the Kaplan-Meier estimator. I was interested to do a little research on this. The one thing I know about the Kaplan-Meier estimator is the paper that published this estimator is one of the most cited papers in all of science. So it's in the top 100 at least of the most cited papers of all time. What I was interested to find out that Kaplan and Meier actually submitted this idea separately. They both submitted the same thing separately in 1956 to the same journal. Crazy, right? And the journal editor contacted them and said, "Hey, why don't you guys work on this together?" They did, and they published the paper. Apparently, they didn't like working with each other. It was not exactly a famously upbeat collaboration between the two, but and Kaplan, the first one, says that the second one actually deserves all the credit. So I don't know what the issue was. But the Kaplan-Meier estimator, very famous in statistics, one of the most cited papers out there. It's a method that we can use to estimate the true survival function. The basic idea of it is, which is kind of simple today, is that it really accounts for censored observations in the right way. So how it works is that the Kaplan-Meier estimator will only change at event times, not survival, not censored times, event times. And this creates, it looks like a step function. So it'll be constant. And then when there's event time, you'll see a little decrease, constant, decrease. And if the event times happen very close together, you can see that. How much of a decrease there is depends on the number at risk and how many people died at that particular event time. Usually this top number is just one. The censored observations, they contribute to this model through the at risk. So they are counted as at risk up until they are censored, and then they're simply dropped from the at risk set. So it's a really interesting way to do it. Seems kind of intuitive now that that's how this would work. But yeah, it's a famous paper and a very highly used method in statistics and survival analysis. So let's see how we do this in R. The first thing that we have to do, we don't have to do this. We can get we can run the Kaplan-Meier curves without it. But just to note, the survival package, it has something called a survival object that it uses for all the regression, Kaplan-Meier curves, log rank, all the things that we have. They use what's called a survival object, and it's used in some of the downstream analysis. The survival object is created right here. So we have this, we're using mutate, survival object, serve, and we give it the time. This is the total at-risk time. And then we give it the, we tell our how do I know the event occurred versus it's censored? So we say, all right, if status equals 2, that means the event occurred. And then we know that that's the way it is in the data set. 2 means dead, 1 means censored. So this creates this survival object. It's going to be different. It's not a character variable, it's not a factor, it's not a number, it's something that's a little bit different. We can see what the survival object looks like down here. They just look like numbers, but no, the plus for this third individual, why is there a plus? Because that means that that patient was censored. 10, 22 plus, this patient was also censored. Everyone else had the survival event. So this is the object that we'll use in downstream analysis. We can also just specify this when we're doing the analysis. The only other thing I'm doing here is just creating factor male female. This is a look at the distribution of the follow-up times for those that were censored, the blue, and those that had the event in red here. Let's get to the Kaplan-Meier curves. So this is a standard way to estimate the survival function. How we do this is we use the serve fit function, and we create this survival object, tell it the at-risk time. Okay, how do I know when people died? And then we just use tilde1 here and give it the data. And then here, when we print, we get some basic information. So let's go to R, and I got a warning message here, but it does. I do have the long data set, so maybe I didn't need that data part. So I'm going to go all the way down to that Kaplan-Meier curve portion. I'm going to run everything before this. And then I'm going to run this Kaplan-Meier curve. So we get some basic information right off the bat. It tells us the sample size, how many events occurred, the median survival time, and a confidence interval for that median survival time. What most people want to do with Kaplan-Meier curves is you want to plot them. So here we can create a plot of our Kaplan-Meier curve, and we see the result here. So some of the features of this, let's actually run this in R so we can see it a little bigger. It's a little small right there. Okay, so we have our plot here. I'm just going to zoom in. Boom, there we go. Um, so some features of the Kaplan-Meier curve here. It is a step function, as I mentioned. So it's flat, and then it just has a um, number of jumps down at each point. The jumps are smaller early on than they are later. So you see later these jumps get bigger, and that's because the at-risk set is smaller. Um, so we see early on here the jumps are really, really small for this top left portion. Um, you notice these tick marks here. They start right here and kind of go down. You see a lot of these tick marks. These are when there is some person that was censored. So there's a tick mark every time there was a somebody dropped out of the study, or maybe the study ended for that particular person if they entered in late. The survival function doesn't jump down at the tick marks. That's because no events occurred. But that does change the at-risk set. Um, the dotted line here is at 0.5, so that's going to represent the median survival. And they gave us the data for that up above. The dotted lines, these are confidence bands. So they are going to tell us, how certain we are about a particular at a particular time, yeah, how certain we are about a particular survival probability. So the median survival is right here. I forget what the value of it was, but say 325. And so our estimate of the survival right there is 0.5, but confidence interval is almost to zero point 0.6 and down to 0.4. So there's some width to that confidence interval there. The uncertainty is going to grow over time in general, but you don't see that happen too much right here. But we're going to have a lot more. We're going to be a lot less certain about things as we go on because we have less patients in the study, as Chad brought up earlier. The right tail particularly is going to be the least reliable. We don't have a lot of patients then. There's not a lot of events happening. So really, the more reliable stuff is going to be early on in the study. So this is something that's important for our modeling that we'll do later on. So here we're going to do Kaplan-Meier curves by sex. Same thing that we had before. I'm just putting that sex label in there. It's printing, giving us the median for males and females. And now we can see plots of the Kaplan-Meier curve for males here in blue, for females here in red. If we wanted to look at this bigger, let's run this. Okay. And zoom in. Okay, so we can see the differences between males and females. So the sample size shrinks here, obviously, because we don't have as many in each group. We have 138 males and 90 females in this. So there's going to be more flat portions, particularly for the females. No events happening there. That's happening because the survival is better for females, and also the sample size is going to be quite a bit smaller. Okay, so let's go back to the notes and we'll talk about the log rank test. Okay, we talked about the features there. All right, the log rank test. This is what you can use to compare two or more survival curves. It's a formal test to compare. We have two groups of individuals, particularly. So it's not something we use for a continuous variable like age. It's something we can use for a binary categorical variable. The null hypothesis is that the two survival curves are the same for all time points. And that's a big assumption. So when we reject the null hypothesis, what we're saying is the survival curves are not the same at all time points. That doesn't mean they're different early on or they're different later on. They could be the same early on and different later on. So the study that we were just looking at, maybe the survival probabilities are the same for the first 100 days, and then they're different. When we reject this, remember, it's a big assumption that the null hypothesis is making. Doesn't tell us when this assumption is violated, just tells us that, hey, they're not all the same. But it's a great procedure. So the Kaplan-Meier curve and the log rank test, two of the most used statistical procedures because they're wonderful. One thing about the Kaplan-Meier curve that I didn't mention is it's a non-parametric method. It doesn't make any assumptions about the distribution of the data. It makes some assumptions on the censoring, but not any assumptions on the distribution of the data, which is incredible. That's why it's so used. Log rank test, the same thing. We don't have to assume normality or log normality or anything like that. So it's a great procedure, and that is mainly because of that non-parametric aspect to it. How does it work? Well, what the log rank test does is it compares the observed number of events in each group to the expected number of events if the two survival curves were the same at every time point. So it ends up being, honestly, a little bit like a logistic regression at every time point. So looking at, all right, is the observed number of events that we've seen so far equal to what is expected if these survival curves are actually the same? So departures from this will lead us to reject the null hypothesis. And again, it produces a p-value. Small p-value means the survival experiences differ between the groups in such a way that it probably did not occur by chance. So the survival differences that we're seeing are not due to chance. Excuse me. How do we do this in R? Well, we've basically done it with what we just ran for sex. We just didn't look at the results of the log rank test. So let's look at that. So we created this survival fit by sex object, and to do the log rank test, we just have to look at that up. So this is the same thing that we did up there. We're just looking at what we created. So we did this survival by sex, and this we plotted that there, and the oh, I'm sorry. So it is a little different. I'm sorry. This is serve diff, not serve fit. My mistake. Serve diff is a little bit different than the serve fit that we had before. So when we want to do log rank tests, use the serve diff function. All the other code is the same as we had with the serve fit. And here I'm just looking at the results of that. So we have the sample sizes. We have how many events were observed. So for males, 138. we observed 112 events. For females, 90, we observed 53 events. So then it says, all right, how many events should we have observed? What is the expected number of events if these survival probabilities were actually equal? And for the males, we should have observed 91 events, not 112. For females, we should have observed 73, not 53. So clearly for females, we have a lot fewer observed events than expected events. For males, we have a lot more observed events than expected events. This would lead us to believe that the survival probabilities are different between these two values. So this is used to create a chi-squared statistic and a p-value. Here, p-value is very low, so that is evidence that the male and female survival curves are different. Going back to the survival curve that we have, we can look at this in zoomed in. So it's not surprising that the log rank test finds that the survival curves are different. They do appear to be different here. Towards the end, they get to be more similar. And there's not a lot of data towards the end, so we don't want to pay attention to that too much, but this could happen. We could get a significant log rank test when the survival curves are different, say from 100 days to 400 days, but then they're the same afterwards. Again, the log rank test doesn't tell us where the differences are. It doesn't tell us that there are differences everywhere. It just tells us that there are some differences. So the null hypothesis is that the survival curves are the same everywhere. There's no difference in the survival curves anywhere on over the length of the study. We're rejecting that. All right, there is some differences in the survival curves that we get. So there's that. Let's look at this a little more carefully. So here we get again the number of the sample size, the number of events, and then we get the median survival time, which I've introduced but not talked about a great deal. In survival analysis, we're more interested in median survival than we are mean survival or average survival. The reason why that is because averages are going to be sensitive to large observations. So if somebody survived 3,000 days, that's gonna sway that average. The median is not going to be swayed by those outliers, those large observations. So because survival time is a highly skewed variable, we report median way more often than we report mean when we're talking about survival analysis. So for males, the median is 270 days. And again, that has a nice interpretation. So we can say, all right, in this study, males, 50% of them, at least 50% survived over 270 days. So it has a nice interpretation. We get a confidence interval for that, 212 days to 310 days. And for females, median survival, 426 days. So a lot different, a lot higher. 150 days, so about 5 months longer. Median survival is about 5 months longer for females versus males, quite a bit. And we have the confidence interval for these as well. We got this when we did the the overall survival analysis. That told us, all right, median was 310 days. Confidence interval was 285 to 263. And we can actually see this on the survival curve. That'd be better if we do the larger one. I'm going to go back to the first survival curve, which has those confidence intervals on there. So the median was 310 days. Boom, that would be right there. The confidence interval, 285 days to 300 and whatever it was. So we can see that confidence interval from this survival curve that we previously estimated. We don't get the confidence bands when we do it by sex. I think you can plot them on there. It can get a little busy when you have like, so that would be 6 lines on this curve, and they're step functions, so it can get a little messy. So we just showed the estimates here, but we can get those. So a good number of a good median survival for both of these. So as I mentioned, median survival, this is what we're going to use over mean survival when we're doing survival analysis. Also, the mean is going to require the full distribution. So a nice thing about survival analysis, what we've talked about so far, it's non-parametric. It doesn't assume a distribution. So that's a nice thing that is one reason why we like median over mean. Right skew I mentioned. If the median's estimable as soon as the curve crosses 0.5, even if many participants are still censored. So one caution, if fewer than half the group experiences the event, we're not going to be able to observe the median. So if you have a situation where very few patients experience the events, there can be situations where we can't estimate the median. It's not always estimable. We have to at least see half the participants experience the event in order to estimate the median. But once we do, it's something that we can estimate. And really, the main thing that we usually get out of a survival analysis. So far we've talked about survival analysis, censoring, Kaplan-Meier curve, log rank test. We'll come back in the second portion of the morning, and we'll start to talk about some of the regression models that we can run, and then we'll start talking about what we'll work on in the afternoon. Let's take a little break here. It's 10:58. We'll come back at 11:15, and we will pick up with the Cox model. Okay, so let's start with the next topic, and this is where things get really exciting for us because it's when we can start to do some regression analysis. So the methods we've gone over so far, Kaplan-Meier curves, log rank test, as I said, and this is not hyperbole, two of the most used methods in all of statistics. What are some of the limitations of them? They cannot adjust for confounders. So the observed differences in the survival between the groups may be due to a third variable. We saw this in the smoking and coronary heart disease relationship, that when we adjusted for age, the effect of smoking got a lot stronger. So age was a confounder there because smokers tended to be younger in that population. So adjusting for confounders, very important. And it's something that we will want to do when we're doing analysis. They work for one or two categorical grouping variables. Can't be used for continuous predictors. That's going to require a regression model. In this situation we just did, females survive longer than males. But is this in this data set, do they also have better performance scores? So are they healthier going in, or is it truly sex that's a prognostic factor? So this is what we're going to try to find out through looking at another model here. So the standard regression model that we use is the Cox proportional hazards model. And we talk about most cited papers in science. Cox proportional hazards model is right up there with Kaplan-Meier. So this model, this is why we introduced the hazard function earlier, is because of the Cox proportional hazards model and how it works. So what this does is it puts predictors directly on the hazard function. And particularly the log hazard function is a linear function of the predictors that we have in our model. How do we model the hazard function? We start with the baseline hazard rate. So this is the hazard rate for participants when all the predictors are equal to 0. The really nice thing about the Cox proportional hazards model is that this baseline hazard does not have to be specified. It's completely unspecified. So it can be a bathtub shape, it can be increasing, it can be decreasing, it can go up and then down, whatever we have. This is what makes the Cox model so special, is that we have this semi-parametric aspect to it. The the coefficients that we get out, these betas, these are going to estimate the hazard ratio for a 1 unit increase in xj, holding all the other variables that we have in our model constant. The predictors shift the baseline hazard up and down, or the hazard function up and down by a multiplicative factor. So we're always looking at the ratio of the hazard functions. So what we'll get back is something like, all right, the hazard ratio is 1.3, something like that. If the hazard ratio was 1, that would happen if the beta coefficient was equal to 0. That means xj, no effect on survival. If the beta j is greater than 0, leads to the hazard ratio being greater than 1. That means higher increasing x is associated with a higher hazard, worse survival. So if we're talking about age here, if it's a positive beta coefficient, older folks, higher rate of failure, lower survival. And then, of course, we have the opposite. Negative betas, hazard ratio is less than 0, lower hazard, better survival. For example, if we get a hazard ratio equal to 2 for a predictor, that means that participants with that predictor have twice the instantaneous rate of failure at any time point compared to the reference group. As with odds ratios, we commonly want to rescale these hazard ratios to meaningful units. So a 10-year increase in age, 5-point performance chain, so on and so forth. So hazard ratios are going to relate our coefficients to the rate of failure. Now, a higher hazard rate, worse survival. There are some studies where the way the event is defined, having a worse survival, a higher hazard is good. So it's important to differentiate these. In the study we're looking at, higher hazard is bad because higher hazard, higher rate of death. If in the pregnancy studies that I used to work on, higher hazard was good because higher hazard meant you were getting pregnant quicker. Some of the early COVID analysis, the drug they were looking at how long does it take for a person to recover with the drug, without the drug. The hazard was positive there. That meant the drug was associated with a higher hazard, but that was good because our time to event was recovery. So a lot of times our event is not something you want to get, but there are some times when the event is something you do want to get. So this better and worse is sometimes, can sometimes flip. Sometimes a higher hazard means better outcomes. Lower hazard can mean worse outcomes. Can go either way. So you have to connect this with your with the example that you're working with. How do we run this? I guess first we're going to look at why we need to use this Cox proportional hazards model. We got females surviving longer than males. We saw this up above, but is it something else? Okay, is it something like the ages were different, or this ECOG score, weight loss maybe is this something that's actually playing a role here? So here we're looking at some of these variables. Do these variables have an association with sex? And we see that there is some differences in mean age. Males tend to be a little bit older than females, a couple years older on average at the start of the study. So that could be some of that effect that we saw. The ECOG score, a little bit higher for males, so that would go the opposite way, but overall they're relatively similar. We didn't adjust for weight loss, but we do see some differences in weight loss here too. So that's something that we could have looked at. You see the formula for the Cox model: hazard function, baseline hazard function, EXP to all our covariates, beta 1 x1 plus beta 2 x2, so on and so forth. Again, the baseline hazard function is left completely unspecified. It's a nice thing. The quantity of interest, we're going to exponentiate these beta coefficients, and this is going to tell us what the hazard ratio is for a 1 unit increase in XJ. Another thing that's nice about this model is that we actually get some quantification. We get something that quantifies the difference. When we did the log rank test up here, we found there was a difference. We don't get any quantification. We can tell that females survive longer than males, but how much longer? We have some medians here, but we didn't have anything like a hazard ratio that we're going to get down below. So that's another nice thing about the Cox model. So we can even run it just on sex because we want to have some quantification, some other quantification that we can display and show people. Okay, so how we run the Cox proportional hazards model is to use the Cox pH function. We're still using this serve argument where we give it how long the person was in the study, tell it when the event actually happened, use the tilde, sex label, data equals long. So the code here is very similar to the log rank test that we had up above. Exact same code in the middle. Just instead of using serve diff, now we're using Cox pH as our function on the outside. Here is a summary of the Cox proportional hazards function. We get the number of subjects, tells us the code that we used, number of events. Here we get our beta coefficient for sex. It is negative 0.531. They also exponentiate the coefficient for us. That's nice because we will want to exponentiate these. Standard error, z value, we get our p-value, highly significant. Okay, there does appear to be some impact. Go down one, we get some more information. Again, the exponentiated coefficient, 0.588. That's less than one. So that indicates that females have a lower hazard function. So they are surviving longer. So it says female right here. So this is going to be the effect of being female versus male. 0.588, less than one, females surviving less than males. They also give us the exponentiated negative coefficient. So if we wanted to know, what if we had flipped this around and we had females as the referent, males as the comparison group, okay, we get the coefficient of that right there as well. They also give us by default 95% confidence interval, which gives us an interval where we're 95% confident that the true value is going to be somewhere between 0.4237 and 0.816. Here, I'm just repeating those values that we already had using the coefficient function and the conf int function that we've used before, exponentiating those and rounding it, and we see the same information that we had. So the unadjusted hazard ratio for sex, 0.59, which indicates that females have roughly 41% lower hazard of death. We could say 41% lower risk of death than males at any particular time point. This difference is statistically significant. This is consistent with the Kaplan-Meier plot and the log rank test. Okay, the log rank test gave us the same information. Usually will be very similar. They're not going to be identical though. All right, let's move this forward to what we're interested in is not just using sex, but actually adjusting for some other variables. So here I'm going to look at age, and I'm going to look at proportional hazards of this pH ECOG variable. I'm going to create a data set that only has complete cases. So get rid of all the anybody that has any missing values there. This only drops one person, which is nice. The weight variable has more missingness, so it's nice to only have one person that we lose here that has a missing value somewhere in here. How we run the Cox model here is similar to what we had before. We're just adding age and this pH ECOG to our code, and again, the output is very similar. We have the sample size, the number of events. The coefficient is very similar to what we had before. Before we had negative 0.53. Here we have negative 0.55. So it did not change much. Age, the coefficient is positive, not statistically significant. pH ECOG coefficient is positive, and it is statistically significant. Again, we get our hazard ratios with these, very similar for the sex coefficient. pH ECOG has a positive coefficient. Hazard ratio is about 1.6, and we have the confidence interval for that as well. Yeah, so with sex, 42% lower hazard for females versus males after controlling for age and performance status. This did not change. So the unadjusted and adjusted were very similar, which tells us that the sex difference that we saw previously was not attributable to age or performance score. They were not confounders in this situation. Age has a relatively small effect. If we scale it to 10 years, 12% difference not significantly different from one in this situation. BHECOG ends up being the strongest predictor here. So it's associated with a roughly 50% increase in the hazard of that, excuse me, 59. So it's about a 60% increase, I meant to say. Um, so, and this ECOG variable, remember it was, if we go all the way back up to the top to remember the coding here, 0 for fully active, 1 for restricted but ambulatory, 2 for in bed less than half the day, 3 for in bed more than half the day. So this is a very strong predictor. Going from fully active to restricted, that's a 1 unit change. And here we see that there's a 60% increase in the hazard for death and the risk for death. So if we, because you could have a 2 unit increase going from fully active to all the way down to in bed but ambulatory. And then the hazard ratio is about 2.5 times. So this is a very strong predictor in this particular assumption. Comparing nested models. This is something we did with logistic regression, linear regression. We can do it here, doing the same way. So here I just fit another model where I removed the pH ECOG variable just as a demonstration. Same function, same ANOVA function. We get a highly significant p-value, and that indicates that the reduced model is not as good as the full model. So not surprising because this was a highly significant variable in the model that we just fit. So I wanted to look at this. I was just curious. Sometimes when I'm going over these things, I think of some other things that we could have run with this. So I'm going to go down to this Cox model here. And I think this is a good example. So I'm going to run this this model that we had. So that's the same thing that we just ran. And then I'm going to run another version of this. This time I'm going to make pH.ECOG. I'm going to turn it into a factor by just putting factor around here. Because this variable is kind of like a factor. There is it's ordinal, so there's some ordering to it, but it is 0, 1, 2, 3. So we could look at this as a factor instead of looking at it as a continuous variable. So as a continuous variable, we're assuming the change from 0 to 1 is the same as the change from 1 to 2, the same as the change from 2 to 3. When we do a factor, it will not assume that. So let's take a look at that. Just as we were going through that, I was a little bit interested to see what we find. Okay, so we see the coefficients here. This is the coefficient for 1. So this is comparing 0 to 1. The coefficient is 0.4. This is the coefficient comparing 0 to 2, and it's 0.9. This is the coefficient comparing 0 to 3, 1.9. Okay, so what do we see here? Well, previously, the coefficient we had was 0.46. Okay, so going from 0 to 1 is a 1-unit change. And our coefficient's not equal to 0.46, 0.41. Very close. It's not very different. Going from 0 to 2, that's a 2-unit change. Here we have 0.9. Previously, 2-unit change was 0.46 times 2, about 0.9. So this right here does not really change. The major difference we see is going from 0 to 3, where previously that would be 0.46 times 3, which would be about 1.35. Now we have it at 1.95. So going to 0 to 3 seems a little more drastic. However, it's not significant here, probably because there's not a lot of people in group 3. So it's kind of challenging to tell. So I was just curious at looking at this to see if maybe there was some, drastically different things that we find. We don't. I think this is very consistent with what we found previously. A little bit lower here, but when we look at the standard error, so the difference is 0.05, standard error is 0.2. So it's well within a standard error. So I would probably go back to the continuous version of the model. Just curious, sometimes when we're going through these things, I think, hey, what if we use that as a categorical variable? And we can compare these using the ANOVA function, as these models are, in fact, nested within one another. I had to think about that for a second. And not significant, so that means we would like the more simple model. Now, why are these models nested? Because what can happen is here we got 0.46. One situation where we can get the exact same thing here is if this coefficient was exactly 0.46, this coefficient was exactly 2 times 0.46, this coefficient was exactly 3 times 0.46. So this model down here can give us the exact same thing as this model up here when all these coefficients are the same. So they are in fact nested. And we see that not significant. So the factor model is not better than the continuous model. Okay, thank you for indulging me and into looking at that. Okay, still got a few minutes here. There are some assumptions to the proportional hazards model, mainly the proportional hazards assumption. So interesting story here. There was a lawsuit in 1993 brought on against Pfizer. Obviously, we know Pfizer, big company, in terms of a heart valve implant that was made by Pfizer. And it was noticed that there was some failure in this heart valve implant that was happening at a higher rate than competing heart valve implants. Pfizer got sued. So what they did was a survival analysis, and they looked at the rate of failure. And I'm not sure if it was death or just failure of the heart valve implant. That's not really important for us. But they had the rate of failure or death, whatever it was, for the Pfizer heart valve implant versus the rate of death for the competing methods, and was there a difference? So the lawsuit all came down to the proportional hazards assumption. Amazing, I know, right? So they had two statistical experts, the Pfizer one and the one for the plaintiffs, and the Pfizer one said that, well, what was happening was that the proportional hazards assumption was not valid towards the end of the study, and that's why you were seeing differences. So the curves were not different early on, they were different later on. And that pointed to a different mode of failure. So Pfizer was not at fault, basically. But Pfizer lost. The patients won. So they believe the other statistician. So what is this proportional hazards assumption? Well, it just says that the two hazard functions are proportional. They run parallel on the log scale at each time point. So what we assume here is that the difference between the hazard functions between, say, males and females, it's completely specified by this one coefficient. There's no differences over time, okay? There's a constant multiplicative difference in the hazard function. So that's the proportional hazard assumption, that the hazard functions are proportional between males and females for all time. Because if we look at the ratio of these, this baseline hazard function is going to drop out, and all we're going to have left is e to the beta. So this is the key assumption in the proportional hazards model. It fails when a predictor, its effect changes over time. So for example, a new drug may be highly effective early on, then wear off. So the hazard ratio starts below 1, but then drifts towards 1. That would be a situation where the proportional hazards assumptions fail. How are we going to plot it? Well, what you do is you plot Kaplan-Meier curves on a log-log scale. If the proportional hazards assumption holds, the curves should be approximately parallel to one another. All right, we'll see this. When it fails, we have to go to other methods. So let's take a look at this proportional hazards assumption, particularly for females. So we're going to use that Kaplan-Meier sex object. This is something we created when we were doing when we looked at the Kaplan-Meier curves by sex. So this was what we created right here and what we plotted right here. So when we're checking the assumption, we want to add this function C log log. So this is going to help us. This is going to help us determine whether the proportional hazards assumption works. The rest of this stuff is just window dressing, labels, main title, all this kind of stuff. So what we would like to see if the proportional hazards assumption is okay is that these curves should be relatively parallel. So the females are here in red, the males are here in blue. So if these are parallel, the difference between these two would be consistent most of the time. There's always going to be some bouncing around between these two curves. So we don't want to overreact too much when we see, hey, these are not exactly parallel with one another. But here, I think for most of this part, maybe there's a little bit of increase. Clearly, there's some bouncing around going on down here, but there's not a lot of failure times up here, so I kind of want to ignore that. Also, clearly, some weird stuff going on down here. Again, not a lot of failure times, particularly for the on the female side of things. So I want to kind of ignore that. But really, what we want to look at is kind of this situation right here. So if anything, I would say they appear to be getting more similar to one another. So maybe there's a bigger effect early on between males and females, but then the females actually are kind of catching up, and then there's this kind of late jump late in the study. So not perfectly parallel, but I think for most of this, most of the observed time from days 50 up to 500, I think that looks relatively good. But there are maybe some departures down here. So what this may lead us to do is to artificially censor everyone in the data set at a particular value. So here, maybe we want to say it's 750. We just want to censor everyone right there because the proportional hazards assumption, we're not sure about it later on. That's something that we could do if we observe that we're really having some issues there. So again, and remember, this is log days down on the bottom. This is not days. So this first stretch, which seems so long, it's really only the first 55 days or so. And then roughly parallel here, it's a decent, I'd say this is a decent situation. I wouldn't say it's famously working, but seems like it's working pretty well. Okay. So comparing, let's go back, go over all these models that we talked about today. First off, we talked about the Kaplan-Meier curve. Super useful, very nice way to visualize the survival function that you have. Can't adjust for confounders. Can't use it for continuous predictors. It's not going to give us an estimate of the effect size. It will give us median survivals, but it's not going to give us a hazard ratio. We can do Kaplan-Meier curves by group. Okay, certainly if you're doing a study where you're looking at treatment and control, always show the Kaplan-Meier curve by group. Log rank test. It's not something to visually, we don't use it for visual anything. It's a formal test to compare if the survival is equal between two groups. Again, we have median survival from that, but we don't really get any effect size. Also, the log rank test says the survivals are not the same, but it does not say where they are different. Are they different early? Are they different late? Visually, we can tell that a little bit from the Kaplan-Meier curve. The Cox model, this is, we don't use the Cox model to visualize survival, although you can do that from a Cox model. You can compare groups, adjust for confounders. Here you can have continuous predictors, and you get the effect size measures, hazard ratio. What is the ratio of risk between the groups that you're comparing? So all three of these great methods. They all have they have a non-parametric component to it. So log rank test and Kaplan-Meier curve, completely non-parametric. Cox model does have that proportional hazards assumption, but the nice thing about it, again, is this baseline hazard that's non-parametric. Important thing about survival is understanding the data structure and the censoring that occurs. Here we've talked about right censoring, but there are other types of censoring that can be present. Interval censoring is when an event happens between two times that you know. Left censoring, this happens when you have subjects that are entering your study that have already been at risk for the event. The first thing you want to do, estimate the overall survival curve using the Kaplan-Meier. If you have groups, estimate the overall survival curve separately by groups. Compare with a log rank test. These are kind of the first steps: median survival, 95% confidence interval. These are the first steps that you should do when you're doing a survival analysis. Then, if you have to adjust for confounders, you move towards the Cox regression model, where you can include continuous predictors. There, you're going to get hazard ratios and confidence intervals. When you do a Cox regression, it is standard to look at the log plot where to check the proportional hazards assumption. You want to see roughly parallel curves for the Cox model to be appropriate. Lastly, some of the key quantities. As I said, median survival with confidence interval for each group. Log rank test, if you are looking at groups, hazard ratios, both unadjusted and adjusted with confidence interval. Very important to report not only the sample size, but the number of events. So that's going to be a key quantity. If you don't have enough events, it's very hard to estimate survival. It's hard to estimate median survival. So what drives the power of a survival analysis is not really the number of people in the study, it is the number of events that you have in the study. That's a much bigger driver. When we come back after our lunch break, we are going to analyze this same lung data set ourselves. At first, you're just going to be repeating some of the overall survival that we did in the morning. Then you're going to be looking at comparing some groups. We're going to have some different groups than we looked at here initially. So be able to look at those, run some Cox models, run some Kaplan-Meier curves by group, and see what type of results that we get. We will meet back here at 1 p.m. If you have any questions in the meantime, or if you want to start on the lab, go right ahead, put those questions in the chat, and myself or Yanan or Elena will be able to field those for you. So have a great lunch. I will see you back here at 1 p.m. Nice, wonderful. Welcome back to the afternoon. I hope you had a nice, wonderful lunch there. And we are going to get to our lab portion of today's survival analysis. You have survived so far, just a little bit to go for this week. Before we get started, I should remind you that all these things, let me make sure I'm getting everything. So all the sessions are recorded. They are put on the YouTube channel. Also, at the end of the week, we have a survey that we send out to everybody that is in Qualtrics. After you fill that out, we get the data. It's all anonymous. It's very important for our annual reporting to our funding agency, getting feedback from y'all and figuring out what worked, what doesn't work, because this is something we want to do on a yearly basis. So we'd love to get your impact to help this workshop be the best it can be. A reminder about your lab. So if you did at least 4 of the labs and emailed them to Elena, you will get a certificate with your name and my signature on that to give you a little recognition for completing the course in terms of doing at least 75% of the labs. I think that's all the announcements I have. So Elena or Yanan, if I'm missing anything, please let me know. Okay. All right. So today's lab, what are we going to do? We're going to use the same data that we used in the morning. So you can open this up. You can open up the lab up directly, or you can copy and paste this into your R window. I'm going to open my R Studio up. Let me just get to there we go. Okay, what am I doing differently here? So we have this group variable, this ECOG group, fully active, ambulatory, less than 50% in bed, more than 50% in bed. We're also creating this PAT.Karno group. If the Karnofsky score is greater than 80, just poor versus good, see what the impact of that is. And we still have sex. So one thing, those groups that we had, the ECOG group, we noticed that the confidence in, or there was a lot of uncertainty in when we did the factor model where we compared 0 versus 3. And I always say there's only one person that is in that 3 group. So obviously that's not a group that we would want to separate out in any way. So here I'm using the factor collapse function to collapse this from a 4-factor variable into a 3-factor variable. The new 3 factors will be, still have 0, which is fully active. We'll still have 1, which is ambulatory. And then we'll have the 2+ group, which will be non-ambulatory, which could be either that 2 or 3 in the initial coding. So now, once we make this new 0, 1, 2+ group, we have a little better sample size in all of these groups that we have. Another thing I wanted to mention is that the Kaplan-Meier's we did in the morning, we did them by sex. We can also do these by this grouping variable here, where we have 3 different groups. You don't need to change anything in the code to do that. So that's really nice. So we have our 3 groups here. The median survival time for the fully active, 394, a little over a year. Ambulatory, about a month under the year. And the non-ambulatory is about 6 months for the median survival. We have confidence intervals for each of these. Kaplan-Meier curves, boom, we get these as well. So the 0, that's the fully active group. Green here, red. And once we get away from the initial 100 days or so, seems like there's a clear ordering where those in 0 are surviving longer than those in the group 1, and they're surviving longer than those in group 2. It is interesting that the fully active group has a lower survival. It kind of dips down here early on. Not sure why that is. It's probably not causal. It's probably something else that we're getting there, but sort of an interesting finding. But for the rest, the ordering of this is pretty clear. Log rank test. We can also do this with 3 groups. We see that in the fully active. We observe 37 events. If all the survival curves were equal, we would expect 54. For the ambulatory, we observed 82. If all survivor curves were equal, we would expect 83. So we're pretty close on this, which makes sense because this one's kind of in the middle. So if they were all equal, the survival would probably be pretty similar to what we get with ambulatory. And then for the non-ambulatory, we have a lot more events than we would expect, highly significant. So we get a small p-value, confirms that the survival is different beyond the groups. The differences are more than we would expect based on chance alone. Okay, now we're going to get to the exercises here. We're going to do these similar to usual. One little difference. So skip this first one. This is just looking at the data. And we're actually going to skip the second one also, because this is just repeating the what we did in the morning, just the overall survival curve. Something we want to do, but you can just obviously just copy the code from the morning to get that. So the first one that we're going to work on is exercise 3. So here we're going to use that Carnot group and get separate Kaplan-Meier curves based on that. So in the morning, we did this by sex. So I'm just asking you to repeat what we did in the morning to get separate survival curves by this Carnot group that we create right here. So this variable, we haven't looked at that variable yet. So separate survival curves there, plot the curves, legend, similar to what we had with sex, and then run a log rank test based on that. This says sex. I didn't mean sex here. I meant this Carnot group. So do we see any differences by that variable? Intuition, what does a small p-value tell us? What does it not tell us that the Cox model will? So just some of those difference in terms of the effect size, the measure of that. We're also not going to do exercise 4, so I'm going to challenge you a little bit here to do exercise 5, which is going to be a full regression model. We did something similar to this in the morning, so it's not a huge stretch. So in the morning, we did this model with sex, age, and pH ECOG. So here we're going to do something similar. Sorry. We'll do something similar. We'll still have sex, age, pH ECOG. We're just going to add weight loss to the model. So adding another variable to the model. We'll do drop NA. We are going to drop some more participants here because weight loss is missing, I know, on at least a few subjects in the data set. So then the first one, you're going to do separate survival models for all 4 variables under question. So this will give us the unadjusted hazard ratios for each of these and the confidence intervals. Then we're going to do a full Cox model, which will have all 4 predictors. Again, we'll get the hazard ratios for those. So that is going to be similar to how we did this down here. In our example, we're going to use ANOVA to test this full model, which will have all 4 predictors, to a model that does not have weight loss to it. So we'll fit another one to see if there's any difference. And E is just a repeat of what we did down here. So that's not it's not anything challenging. It's just using the same code we did. There's not going to be any difference because it's not model specific or anything. And then just, hey, the hazard ratios we had in the morning were 0.59, 0.58. With this full model that has weight loss, do we see any difference in those hazard ratios? So does weight loss add anything? We had age and ECOG in the morning. So the only variable we're adding to this one is the weight loss variable. So just 2 questions here, exercises 3 and 5. Exercise 5 is a challenge exercise, but it really follows what we did in the morning pretty closely.